I'll go ahead and get started. So I'll start off by introducing myself. My name is Matt. I'm a senior here like all of you here at UCF. I'm an IT major. I work as a software developer during the day. This is kind of a branch topic off my original topic. I had covered Moore's Law in my first presentation, and I had come across a solution to extending the performance doubling promised by Moore's Law. It was a small topic called domain-specific architectures, and I thought, like, what better opportunity to learn more about it than to do a presentation on it. So without further ado, I'll just kind of hop in. So outline for this presentation, I'll define what domain-specific architectures are. I'll describe the motivation of this approach. I'll also talk about why general purpose processors fall short with the ending of Moore's Law. I'll explain how exactly domain-specific architectures can outperform traditional processors. And I'll go over a few case studies of a few popular implementations in industry. Some pretty interesting stuff. Can't wait to get into that. So what are domain-specific architectures? The idea is that you can design a computer architecture in such a way that facilitates a higher efficiency in processing within narrow areas. And you're supposed to be able to run in a specific domain of computation, whereas a general purpose processor may only be able to walk, so to speak. And while any given domain-specific architecture may lag behind in speed compared to a general CPU in almost every broader category, the domain-specific architecture will excel greatly within a single category. So it's really,
Matthew, are you so kind to explain what this term computer architecture means, technically speaking?
What does it mean? I believe it's the at the low level, like design of like how the instructions execute at a very fundamental level, on like the gate level, basically.
Well, so it is a specific is the specification of ISA, instruction set. So a computer architecture means the specification of the instruction set, ultimately.
Okay, thank you for clarifying.
Thank you.
Yep. I'll continue on. And the motivation for these architectures, mainly it's going to be the end of the performance doubling, rather promised by Moore's Law. We are reaching the end of Moore's Law, and so we need a new way to kind of continue that really cool performance doubling that we've had for so many years with Moore's Law. And on that same note, the end of Dennard scaling and Andel's law marks the end of major innovations for performance improvement in general purpose processors. And the approach to domain-specific architectures assume that major performance increases must be done with domain-specific hardware acceleration. And this is all championed by John Hennessy and David Patterson. And they personally believe that domain-specific architectures are the most pragmatic way forward regarding the continuation of Moore's Law. And so how exactly can these domain-specific architectures improve performance? Well, for one, they eliminate unneeded accuracy. So by moving to a lower precision floating point, you can go from using 32-bit and 64-bit integers down to 8-bit and 16-bit integers. And you're also able to use a more effective use of memory bandwidth, and you can capitalize on that by using that saved space to build bigger ALUs and bigger memories. Continuing on, you're also able to use more efficient parallelism within a specific domain. Specifically, you're able to have a greater shift towards simple instruction multiple data SIMD in order to simplify instruction execution. Now, with all of this, you do lose flexibility, but you gain efficiency. It's a very common theme here in domain-specific architectures. And you're also able to use domain-specific languages, which are designed for the actual hardware itself. So instead of using something like Python or Java, you can use a super low-level domain-specific language to better efficiently execute code. So to kind of illustrate that in a little more detail, you could consider a basic matrix multiplication with languages that have a varying degree of closeness to a specified domain. So this is a very popular example. I'm sure a lot of you have seen it before, but I think it's worth mentioning to kind of drive home the point of how a domain-specific language can really improve performance, going from a really general purpose language all the way down to like a really specific domain specific language. So if we were to consider a problem that multiplies two 4096 by 4096 matrices, each successive refinement in domain-specific language going from further away to closer leads to an improved running time. So if we were to do this multiplication in Python, it would result in and a completion time of about 25,000 seconds. In C, it's much more dramatic improvement. So that would finish in about 542 seconds. You could consider an optimized version of C that utilizes parallel loops and memory optimization. Even more dramatic increase, you have like 3.8 seconds finishing time there. And finally, if you go all the way down to like Intel specific AVX instructions that uses vector operations efficiently, you actually get down to like less than half a second, so 0.41 seconds. So you can kind of see like as you go from more general to more specific and domain specific approach, you get a much more dramatic increase. In fact,
But
you know,
if you allow me to interrupt for 1 second.
Yeah.
So people have realized that it's very useful to have vector processing instructions. So this is what AVX is. What they designed, they added to the regular instruction set. These are called multimedia extensions, instructions which could, first of all, could operate SIMD execution, single instruction, multiple data, which means vector mode, instruction which could operate on different data, different types of data, 8 bits, 16, 32, 64, and so on and so forth. So this is what AVX is. So the regular instruction set of Intel was expanded with the so-called multimedia extensions and with vector extension. Sorry for the interruption, but I wanted to point out that this was one of the steps which preceded the domain-specific architecture approach.
Yeah, thank you very much. It's really cool to kind of hear about it from a professor. So continuing on, I guess to wrap this all up, the result is that you get a 62,000 times speed up in execution with a more narrow domain-specific approach. So that kind of outlines the real advantages here to a domain-specific approach. And to talk about why general purpose CPUs fall short, or where they do in particular, they really fall short in the processing of deep neural networks at scale. And this kind of leads to the largest commercial application for domain-specific architectures being the processing of deep neural networks. And this is an area where designing a narrowly focused architecture can actually make a lot of sense. And as you train these deep neural networks on conventional CPUs, especially at scale, that becomes very, very expensive. So the domain-specific approach is a much more cost-effective way of doing things as well. Some popular examples, perhaps most notably, is going to be the tensor processing unit from Google. There's the Intel Loihi chip, which is still kind of early days yet, but that's a pretty cool thing. You also have the Google Pixel Visual Core, and you also have the Edge TPU, also by Google, which is kind of like a TPU meant for edge computing. And the common theme here is that these newer architectures are oftentimes designed with artificial intelligence, machine learning, or deep learning in mind. In fact, that's like almost across all of the popular domain-specific architectures that I saw, as they all kind of have like ML applications. So as a first case study, I'll go over the Google's tensor processing unit. It came as a reaction, actually, of the increased computational demands on Google servers. And this was all caused by an increased use of deep neural networks involved in the research by voice feature. And it became a very high priority project for them because their server loads from this feature were just like, it was just totally insane. And they had to build a new architecture to be able to handle the new load on their servers. And the core idea of this architecture is to have a robust system for executing matrix operations using its matrix multiply unit. And the focus is on having it be of a sufficient size, as well as to try and keep it as busy as possible. And on that same token, deep neural networks are very reliant on matrix processing. So it makes sense to design an architecture with matrix heavy applications in mind. And that's a picture of the TPU on the right-hand side, version 1. There's 3 versions now. Version 3 and version 4 is coming out, I believe, in the next couple of years. So this is a block diagram of the TPU. Basically, the genesis of this is going to be the matrix multiply unit on the right-hand side. And after that matrix multiplication is performed, the results are then stored in the accumulators. And then the results are passed to an activation pipeline where an 8 GB DRAM stages those results through some weights and is then stored in a set of accumulators. After that, the results are going to be stored in the unified buffer in the middle of the picture. It's like the blue rectangle. And then from there, some more matrix operations can be performed on that data in the unified buffer, or it can be retrieved from the host interface. TPUs are also more power efficient as well. And especially when talking in terms of scale, TPUs are much more efficient in this area than most general computer architectures. And if you were to look on the right-hand side, you can see 3 different unique servers running 3 different classes of processors. So you have like a Haswell Intel server-based server, and you have a T80 GPU or K80 GPU server, and you have a TPU server. And basically, you can kind of see as the workload increases, the Haswell server and the K80 server are much more power cost not effective. They cost much more power to run as the workload goes up. But with a TPU server, the power kind of remains relatively constant. So the TPUs have a much more comparative advantage in this area of power consumption. So I thought that was important to note. Some more important notes on the TPU. A lot can actually be learned about domain-specific architectures, for example, by considering an alternative design to the TPU. So for instance, if you were to include clock rate, it wouldn't necessarily help memory or help performance if you don't help the memory side of things. So if you just kind of like artificially increase the clock rate of the CPU without optimizing memory on the chip, it doesn't really yield any dramatic increases in performance. And even if you were to replace the GDDR3 weight memory on the board with the GDDR5 equivalent, it would increase the total area of the board as well as make it less power efficient. And I kind of say all this to say that creating a truly superior domain-specific architecture versus a traditional one is often a very nuanced business, and the advantages are often only very obvious at scale. So it's not easy at all to design a really truly advantageous domain-specific architecture. Another case study that I'll talk about is going to be Google's Pixel Visual Core. The motivation here is to better handle image processing on their Pixel and Nexus devices. And unlike TPUs, the PVC is fully programmable. And some of the major benefits are retained here of domain-specific architectures as a class. So you have more efficient power usage, use of a better domain-specific language, and all other ensuing benefits. This is a diagram of how the architecture works for the Google Pixel Visual Core. It's going to be centered around the image processing unit, the IPU. They're on the right-hand side of the screen there. You can see them. The IPU is able to perform stencil computations with its architecture of a stencil processor. And then the line buffer pool underneath it, highlighted in that bluish purple color, acts as the DRAM for the stencil processor. And the key takeaway of this is that the IPUs are optimized for stencil processing, which is a key component of image processing and optimization. A little more on this. Each IPU core has 512 ALUs and 256 processing elements arranged in a big 2D array, as seen on the right. And the final result of a lot of this is that their HDR plus feature, the high dynamic range, can run 5 times faster and at 1/10 the energy cost versus the PVC's predecessor, the Qualcomm 835. So by moving to a domain-specific architecture, they were able to reduce the power that their chips normally take on the phones, and they're also able to run them much, much faster. So it was obviously a very strategic move from Google to move to a domain-specific approach. Another fun fact, this chip can also support TensorFlow as well as Halide, which is a domain-specific language for image processing. And on the right, we have like a graph of processing elements. The hexagons are halo arranged processing elements versus the spheres, which are just like the core processing elements. For my last case study, I'll go over the Edge TPU. Again, Google is responsible for this. The focus this time is entirely on edge computing. With the new explosion in machine learning, more powerful edge devices are needed to process domain or deep neural networks. Now, these edge TPUs specifically are not intended for training. They're meant for inference only. So they can't really like train a deep neural network that efficiently. It's more meant to perform inference at the point of action. And this all kind of takes the processing to the edge, as edge computing kind of implies. And it could be a lot faster doing it this way versus having to wait over a network for a cloud CPU calculation. And massive improvements in inference can be seen from pairing an edge TPU with a simple computer, such as something as simple as a Raspberry Pi. I have the edge TPU microarchitecture kind of laid out here, kind of similar to the Pixel Visual Core. It's organized in a 2D array of processing elements. The operations are executed in a CMD manner, simple instruction, multiple data. Each processing element has memory shared across all of its compute cores. Core memory specifically is for storing model parameters. You can see the inside of the processing element all the way on the right-hand side. You can see like a close-up of what's inside the processing element. And in each cycle, a set of activations are sent to the compute lanes, and the calculation then occurs between the model parameters and the activations. Then finally, the results are either stored in the processing element memory or uploaded into DRAM. I have a graph here that kind of illustrates the advantages of moving to an edge TPU sort of setup. You can see on the bottom, we have MobileNet V1, MobileNet V2. These are deep neural networks. And so if we were to take these deep neural networks, you can take the same 8 general processors, and you can see how well they perform with the edge compute unit paired with it. So you can see the baseline performance of inference without the edge TPU. If you were to look at the blue bar graph, so if you look at the blue bar graph, you'll see like a base performance line of how well the normal computers do without the edge TPU, and the red dots indicate the performance acceleration improvement with the edge TPU. So you can kind of see from this graph that using an edge TPU in conjunction with a general purpose processor is a very advantageous way to perform inference. So it's a really cool application of a domain-specific architecture. And to conclude my presentation, this approach to domain-specific architectures kind of assumes that general purpose processors are the only way forward in continuing Moore's law. They're designed to be very efficient in one specific domain of applications while dramatically sacrificing general performance and thereby flexibility. And they make the most sense at scale, as there is greater overhead in design, manufacturing, and employee training. And it's still relatively early days, but domain-specific architectures will become more prominent as the performance gains from general purpose processors will continue to diminish, at least relative to what they used to be. I have some references here. And if anybody has any questions, I can take them now.